Now if I want to know the changes which are happening in the flow conditions because of my soil sample present in between, what will I do is I will simply install piezometers at the two ends, okay, at the inlet and one at the outlet, and will monitor for the head difference across the 2 points. So let us insert piezometers. Okay, so now I have inserted two piezometers, one at the very first inlet and second at the outlet. So now we will monitor for the head changes across the 2 points. Suppose at the very first piezometer water rises up till this level, okay, and at the second piezometer water will rise up to a somewhat lower level because of the obstruction which is our soil sample is present, okay. This soil sample is acting as a obstruction, or you can say resistance to the flow, okay. That is why this water will have some amount of energy that will be consumed in overcoming this obstruction. Therefore we are clearly observing the head difference. Now let us measure this head difference. Now let us consider a reference line, that is a datum first. In order to measure the head difference, we have to first consider a datum point from where all the elevations will be measured. So let's make one. Okay, so this is our datum, or you can say the zero level. Okay, now we will be measuring all the elevations of different points by considering our datum as a zero level. Okay, so let's measure this. Suppose this height is h1, or you can say h initial, so hi. On the other end, let's say height is up to this much only. Let us assume that this height is hf, or you can say h final, hf. Now we can clearly see that our head is decreasing from this point to this point over here, okay. So there is for sure a head difference, okay, across the 2 points. Now to calculate the head difference, we will use the simple mathematics and subtract hf and hi, okay. So suppose we obtain a value of delta h, okay. So hydraulic gradient is a term that is defined by the effective head or delta h available per unit length, okay. So we will be dividing this delta h by the length of the soil sample, okay. Suppose in our case the length is this, the length will be this much, okay. This is L, okay. So this term is representing our hydraulic gradient, okay. So I think this much is clear. One more thing that I want to tell is that the delta h, that is the hydraulic head, so this delta h is also called the hydraulic or effective head, okay, effective head, which is obtained by subtracting the head availables at the inlet and the outlet points, okay. So this delta h is nothing but this distance from this point to this point. This is delta h, okay. And if if we just relate this concept with our mathematics, that is, if this is our slope, okay, or you can say a slant line, so this will be our theta, okay. So slope of the line is given by tan theta, okay. So tan theta is nothing but perpendicular upon base. So in this case our slope is nothing but hydraulic gradient, okay, hydraulic gradient, which will equal to perpendicular upon base. So perpendicular in this case is delta H, and the base will be L, okay. I hope this thing is clear. Also one important point to remember here is this head, that was HI. This head is constantly available. This head is constantly available up to this point, okay. Also one thing you might ask, or you might have thought about, is why I haven't taken the base as the whole length, okay. Instead I have taken this much length only, okay. So let me make you clear. First of all, this figure, I have made this figure to make you understand the concept only, okay. In reality, let me show you. The case would be like this. Suppose this is my pipe, or you can say a glass tube. This is my soil sample, okay. This is the inflow, this is the outflow. So this is my soil sample, okay. So I will be measuring pressure hovered at across these points, okay, at the very first starting interface and the very last interface, okay. So this head HI, which was available at the inlet, is also available at this particular interface, okay. So this H is only available because in this region there is no resistance available. If we neglect the frictional resistance, so this head wouldn't be destroyed anywhere up till this point, okay. After this point onwards, now the head dissipation, or you can say energy dissipation, will take place in the region of soil, and again the head will be constant up till here. I hope this thing is clear to you. Let's proceed further. Now if I want to know that what is the velocity at this particular point, okay, that is the point at which if a fluid particle will pass, it will have a memory of the resistance that was offered by the soil sample, okay, and therefore its velocity will have changed accordingly. So to obtain the velocity or discharge velocity, we have the following relation that was given by Darcy, okay. So Darcy observed from his experimental results that the discharge velocity is proportional to I. That is, the discharge velocity is directly proportional to hydraulic gradient. What does this mean? That if I increase the hydraulic gradient, my discharge velocity will also increase, or my discharge velocity is a function of hydraulic gradient, okay. So now if I just remove this proportionality sign, I will be obtaining a constant, okay. So this is nothing but Darcy's law, okay, Darcy's law, and this constant K is only our permeability. That is, K is coefficient of permeability, okay. This is the Darcy law, that is V is equals to K into I, okay. But this law is valid in laminar conditions only. You must have heard about the three types of conditions, that is laminar, turbulent and transition. Okay, so if I talk about the pipe flow, okay, so laminar condition is a condition where Reynolds number is less than 2000. Okay, Reynolds number is less than 2000, and turbulent flow is a condition where Re is greater than 4000. Okay, and transition is a condition where this is called turbulent. Okay, and transition is a condition where Re is between 2000 to 4000. Okay, Re is nothing but our Reynolds number, that is, the formula is rho Vd upon mu, where mu is the dynamic viscosity and d is the characteristic dimension. Okay, so in case of flow through soils, if Re is less than 1, then only we can say that our flow is in laminar condition. Okay, so if the flow is not in laminar condition, this law will not be valid. Okay, this law, or you can say relationship, we cannot use, okay, to obtain anything. Now let's try to find out what is my fluid velocity in my soil sample. Okay, what is the fluid velocity in my soil sample? Okay, now if I just make the front view of this soil sample, okay, so it will be something like this only. This is my boundary, these are my soil particles. Okay, these are my solid particles. Okay, and water will be trying to permeate, okay, in a direction perpendicular to the plane of my board. Okay, so water will be trying to permeate or penetrate in a direction perpendicular to my board. Okay, now what will happen? The net area that is available for the flow, the net area, or you can say the effective area that is available for the flow, is only the area that is available will be this only. Okay, will be this only, this white region. Okay, the void spaces are only available for the fluid particles. Okay, from the solid particles there will be no flow taking place. Okay, because it is a solid obstruction to the flow. So this is the effective area, or you can say the effective space available over a section for the flow. So you can say, we can clearly see that this area is less than the total cross sectional area. Okay, suppose this is small a, so this area is less than total cross sectional area. And also we know that you must have studied in fluid mechanics that A1 B1 is equals to A2 V2. This is nothing but equation of continuity. This suggests that discharge remains constant throughout the section of a flowing fluid. Okay, so what will be the product of A1 B1 in this region will be equal to the product of A1 V1 A2 V2 at this region, and this will only be equal to the product of A3 V3 at this region. Okay, now suppose I want to apply my continuity equation at these 2 points. Okay, this is the first point and this is the second point, or you can say the section. This is the first section. Okay, and this is the second section. So what will be the case? My equation will be something like A1 V1, okay, is equals to A2 V2. Okay, this area at 1 is nothing but the total cross-sectional area that is available of the glass tube. Okay, so this will be, let's suppose this is A, okay, and velocity of flow, let's suppose this is V, okay, in the glass tube. Now this A2 will be somewhat lesser than the capital A, okay, or you can say that this is the area of voids. Okay, so suppose A2 will be the area of voids and V2 is nothing but the velocity of fluid in soil sample, or you can say the velocity with which the water or our fluid is percolating through our soil sample. This is nothing but the seepage velocity. Okay, we call it as seepage velocity. Okay, we represent it by the term Vs. Okay, so Vs nothing but the velocity by which the fluid particles is percolating through our soil region. So this one. Okay. So now let us suppose that okay, let's first give dimensions to our section. Suppose this is a square cross section. Okay, this glass tube is having a square cross section of 4 into 4 meter. Okay, and suppose the velocity at this point is 2 meter per second. So our discharge is nothing but area into velocity. So area will be 4 into 4, that is 16, and into velocity 2, that is 32. Okay, 32 meter cube per second is the discharge that is available across all the points. Okay, so now let us solve this equation. So area will be 4 meter into 4 meter into velocity, that is 2 meter per second. So this will be 32 is equals to A2, that is the area of voids into the seepage velocity. Now look here. Here the area was 4 into 4, that is 16 meter square. Okay, so you can have an idea that this 16 meter square is this area. Okay. Let me just put this thing over here. Okay, so this 16 meter square is this pink area. Okay, the area bounded by this pink region. This is 4 and this is 4. Now this white region, okay, this white region, we can clearly say that this area will be less than the total area, that is 16 meter square. Okay, so this area is less than this area. Okay, this A is more and this area is less. Okay, and also we know that Q is constant. So this is my Q, this is my A1 V1 is equals to small a into Vs. Okay, so Q has to be 32. Okay, no matter what are these values, Q has to be 32 at all the points. Okay, so this area is more, so velocity will be less. Suppose this area is 32, so suppose this area is 16 and velocity here is 2. Now this area will be less than 16. Okay, this area will be less than 16. Let's suppose, so let's make an assumption that this small area, I know the value of this small area. Suppose let's make an assumption that this small area is 50% of the large area. So large area I know that is 16, so 50% is nothing but 1 by 2 of 16, that is 8 meter square. Okay, so I have obtained that small area is 8 meter square in magnitude. Okay, this is 8 meter square. Okay, now if I want the product, now this seepage velocity will be, let's suppose this seepage velocity is x. Now if I want the product of these two terms to be 32, okay, the seepage velocity will have to be 32 divided by 8, okay, that will be equals to 4 meter per second. So this thing I think you must be realizing now, our seepage velocity, or you can say velocity of flow, has automatically increased to satisfy our equation of continuity or to satisfy the discharge value. So this seepage velocity is now 4 meter per second, which was initially 2 meter per second, has now become 4 meter per second. And also you can see the product at LHS and RHS is the same, that is 16 into 2, that is equals to 32, and 8 into 4, that is also equals to 32. Okay, we observe a very important and very noteworthy phenomena over here, that as my area decreases, okay, as my effective area for the flow decreases, my velocity increases. Okay, my velocity will increase as my area will decrease, my velocity will increase in order to satisfy the discharge value. Okay, you must have realized this concept in your life. For example, this is a kid who is watering plants. Okay, so he has the water pipe that is connected to a tap. Okay, so this is a water pipe that is connected to a tap and is trying to water some plants. Okay, so what we generally do is we put a thumb over here. Okay, suppose the plant is something far away from our reach, so we will put a thumb over here, and this eventually will decrease the cross-sectional area, and therefore the velocity that will be available at this point will increase, and eventually our plant will get watered over this distance d. Okay, so I hope this thing is clear. Now let us get back to our equation of continuity and try to apply these concepts. Okay, so we know that a1 v1 equals to a2 v2. Okay, a1 is nothing but the area, total area of cross section available, and v is nothing but the discharge velocity. Let's represent it by v subscript q. Okay, a2 is nothing but the void area available. Okay, so let us represent it by small a. Okay, and v2 is nothing but the seepage velocity, so let us represent it by s. So from here we can say that a into vq upon small a is equals to seepage velocity. Okay, now how to obtain this small a? Okay, small a, okay, that is the area of voids. So if we consider our soil sample, okay, so this is our soil sample. Okay, let's say these are the voids which are now filled with water, since the water is the fluid that is percolating through our soil sample, or water is the fluid that is penetrating through our soil sample. Okay, so this water only will be present in our voids. Okay, and all the air will be expelled out of the voids. Now we know a term called porosity. Okay, porosity, which is represented by eta. So porosity or eta is nothing but volume of voids Vv upon total volume of soil sample. Okay, so this is porosity. So if I want to obtain the volume of voids, okay, suppose this is my total volume. Okay, this will be my total volume V. Okay, and this will be my volume of solids. Okay, and the third thing that is present here is water. Okay, and let's say this water is present in voids, so volume of water here will be equal to volume of voids. Okay, so let us just take that volume of void is Vv. Okay, so this is the main volume bifurcation. Now, now look here. Now if I multiply, if I have the porosity eta, I have this value. Okay, this is known. Eta is known. Now if I multiply my eta with my total volume of soil sample, okay, total volume of soil sample, what will I obtain? Now we know that eta is nothing but Vv upon V sample. Okay, so volume of void upon volume of sample. Okay, and into volume of sample. Okay, so this will cancel out. Okay, so we will be obtained with volume of void, which implies that if I multiply my porosity with the total volume of soil sample, I will be obtaining the total volume of voids available in my soil sample. If I multiply volume of my soil sample by the porosity eta, I will be obtaining total volume of voids present in my soil sample. Okay, I think this much is clear. Now what if I multiply eta? Okay, now what if I multiply my porosity with the area of soil sample at any particular section? Okay, in this case area will be same. Okay, that is A only. So what if I multiply my porosity with the area available at any cross section or area total or area of soil sample? So we can see that eta is nothing but volume of voids upon volume of soil sample, okay, into area of soil sample. Okay, I can also write this one as Vv upon V sample upon area of sample. Okay, so volume upon area. Okay, if I talk about the cube or any other body, for example cuboid, I know that L into V into H for a cuboid is the volume, and if I divide it by area, I will be obtaining the third dimension. In case of cube, I know that side cube, okay, side into side upon area. Okay, I will be obtaining the third dimension. So here also I will be obtaining the third dimension only. Okay, third dimension. Okay, now so volume of voids upon third dimension. Okay, so anything upon third dimension will give the area of that thing. So here volume of void, let me write it again, eta into A is equals to volume of void upon third dimension. Okay, third dimension. So this will be equal to so this will become eventually equal to area of voids. Okay, so this will eventually become equal to area of voids. So now I can see that if I multiply my porosity with the total area, I will be obtaining the area of voids. Okay, now we will make the use of this relation over here. Okay, we will be using this relation over here. Okay, so A into discharge velocity upon small a, that is nothing but eta into capital A is equals to Vs. Okay, so this will cancel out. So I will obtain a very important relation, that is my seepage velocity. My seepage velocity is equal to discharge velocity upon porosity eta. This is a very important relation. Okay, what does this relation suggest? It suggests that the very first thing that it suggests that seepage velocity and discharge velocity are different. Okay, they are not same, they are different. The second thing it suggests that the second thing we can observe from this relation is that seepage velocity is more than discharge velocity. We just have seen that if I reduce the area of cross section, my velocity has to increase in order to satisfy the discharge value. Okay. Also from this equation I can observe the same pattern. We know that eta we know that eta is nothing but volume of void upon total volume of soil sample. Okay, so this volume of void will always be less than total volume. Why? Because total volume is only volume of void plus volume of soil solid. So this denominator has the term VV, okay, plus something, and the numerator has the term only VV. So we can clearly see that denominator is always greater than denominator here will always be greater than numerator. Therefore, eta value will always be no matter what, always be less than 1. Okay, so it will be in points. Okay, 0.02 or 0 point something like that. Okay, now if this value decreases, okay, my whole fraction will increase. Okay, the whole fraction will increase. Okay, how? Let's take an example. Suppose my discharge velocity is VQ. Suppose my discharge velocity VQ is 2 meter per second, and my porosity value is 0.2. So what will be my seepage velocity? That is discharge velocity upon eta. So 2 divided by 0.2, that is 2 upon 0.2. Okay, so it will be 2 will be cancelled out by 2, so it will be 10 meter per second. So here also I can see that my seepage velocity, that is 10 meter per second, and earlier my discharge velocity was 2 meters. So my seepage velocity has increased, okay, in order to satisfy the discharge value. Okay, I hope this thing is very much clear now. Okay, we will continue with the permeability in the next lecture. In this lecture, what we have done is we have studied two important relationships. That is first one that is V is equals to K into I. That is, this one is Darcy's law. Okay, Darcy's law. And the second one is seepage velocity is equals to discharge velocity upon porosity. And also we have studied some basic concepts about permeability. Okay, we will continue in the next lecture. Thank you.